Tonight you do not need to solve anything, remember anything, or even stay awake for very long. All you need to do is listen, let the thoughts arrive and drift away again, and allow the story of the universe to move at its own steady speed. Before we ease into it, take a small moment to notice where you are. Are you listening from a bedroom with the lights already dimmed, or maybe from a couch where the day is finally loosening its grip? What time is it where you are right now? Late evening, early morning, or somewhere in between when the world feels especially quiet? It is a fitting question tonight, because this story revolves around time, distance, and numbers that refuse to line up neatly, no matter how carefully we measure them. If you find this calm exploration soothing, or if it helps your thoughts settle after a long day, you are always welcome to like the video or subscribe. It helps this gentle corner of science reach others who may also be searching for something slow, thoughtful, and reassuring. And now, with nothing else required of you, we can begin. Imagine for a moment that you are standing in a vast open field at night. There are no buildings, no streetlights, no familiar landmarks, just darkness above stretching in every direction, scattered with faint points of light. Some of those lights are close, some unimaginably far away, and every single one of them carries a story from the past. Astronomy, at its heart, is the act of listening to those stories and trying to piece them together into something coherent. For over a century, scientists have been doing exactly that. They have been measuring the universe, carefully, patiently, number by number, using the best tools available to them. They have weighed stars, timed explosions, tracked galaxies, and followed faint glows left over from the earliest moments after everything began. And for a long time, those measurements seem to tell a consistent story. The universe is expanding. Space itself is stretching. Galaxies are drifting apart, not because they are moving through space, but because space is growing between them. That much at least seemed clear. But then something subtle happened. As measurements improved and instruments became more precise, the numbers began to disagree. Not dramatically at first, not in a way that set off alarms or caused panic. Just a quiet mismatch, small enough to be dismissed as error, yet persistent enough to refuse to go away. The universe, it seemed, was telling two slightly different stories about how fast it was expanding, and no matter how carefully scientists checked their work, those stories did not quite line up. This is where our journey begins, not with certainty, but with disagreement. To understand why this matters, it helps to step back and think about what it means to measure something as vast as the universe. On Earth, measurement feels straightforward. A ruler, a clock, a scale. Even when precision matters, the basic idea remains the same. You compare something unknown to something known, but the universe does not offer us that convenience. We cannot stretch a measuring tape from one galaxy to another. We cannot place a stopwatch at the edge of space and wait. Instead, astronomers rely on light. Light is the universe's messenger. It travels at a constant speed, it carries information about where it came from, and it remembers the conditions it passed through along the way. When we look into the night sky, we are not seeing things as they are right now. We are seeing them as they were, sometimes millions or even billions of years ago. A distant galaxy does not appear distant simply because it is far away. It appears distant because its light has taken an extraordinarily long time to reach us. By studying that light, astronomers can learn two crucial things. First, how far away an object is. Second, how fast it is moving relative to us. Combine those two pieces of information, and you can begin to describe how the universe is expanding. This relationship between distance and speed is captured in a single value known as the Hubble constant, named after Edwin Hubble. Despite the name, it is not really constant in the everyday sense. It is more like a snapshot, a number that tells us how fast the universe is expanding right now, at this particular moment in cosmic history. For decades, scientists have worked to refine this number. Early estimates were rough, uncertain by huge margins. Over time, with better telescopes and better methods, the uncertainty shrank. The hope was that eventually all measurements would converge on a single value, neat and precise, like the answer at the end of a well-behaved equation. That is not what happened. Instead, two different approaches to measuring the expansion of the universe began producing two different answers. Both methods were careful, both were sophisticated, both relied on solid physics. And yet when the numbers were compared, they stubbornly refused to match. This disagreement is now known as the Hubble Tension, though the name makes it sound more dramatic than it feels from the inside. There was no sudden realization, no single moment when scientists gasped and stared at a chalkboard in disbelief. It unfolded gradually, through papers, conferences, reanalyses, and quiet discussions that stretched on for years. One way of measuring expansion looks at the nearby universe. It starts close to home, using stars and galaxies that are relatively near, at least by cosmic standards. Astronomers measure their distances using a carefully built chain of methods, each one calibrated against the next. This approach relies heavily on observations made by instruments like the Hubble Space Telescope, which has spent decades quietly circling Earth, free from the blurring effects of our atmosphere. The other way looks deep into the past. Instead of measuring distances directly, it studies the faint afterglow of the early universe, a nearly uniform background of radiation left over from a time when everything was hot, dense, and close together. By analysing subtle patterns in that ancient light, scientists can infer how the universe must have expanded over billions of years to arrive at the structure we see today. In principle, both methods should lead to the same answer. After all, they are describing the same universe, but in practice they do not. The difference is not enormous. It is not a factor of 2 or 10. It is a few kilometers per second per megaparsec, a unit that already sounds abstract enough to blur into meaninglessness. Yet the precision of modern measurements is such that this difference cannot be easily dismissed. The error bars do not overlap. The numbers stand apart quietly but firmly. At first, many assumed the issue would disappear with better data. Perhaps there was a calibration problem. Perhaps a subtle bias had gone unnoticed. Perhaps dust, gas, or instrumental quirks were skewing the results. These are reasonable assumptions, and scientists are trained to distrust surprising results until every mundane explanation has been exhausted. So they checked, and checked again. They reanalyzed data. They improved models. They cross-checked instruments. They used different stars, different galaxies, different statistical techniques. The measurements became sharper, more reliable, more constrained. And as that happened, the disagreement did not shrink. If anything, it became more pronounced. This is the moment when a scientific puzzle becomes interesting. Because when two well-supported methods disagree, there are only a few possibilities. One of them is wrong. Both of them are missing something. Or the underlying theory needs adjustment. None of these options are trivial, and none of them are comfortable. Yet they are also where progress often begins. To appreciate why this matters, consider what the expansion rate of the universe connects to. It influences estimates of the universe's age. It affects how structures like galaxies and clusters formed over time. It ties into the nature of dark energy, the mysterious component thought to be driving the accelerated expansion of space. A shift in this number ripples outward, touching nearly every corner of modern cosmology. And yet, despite its importance, the universe itself seems entirely unconcerned with our confusion. Galaxies continue to drift apart. Light continues to travel. Stars are born and die on schedule, indifferent to whether our equations balance. There is something quietly humbling about that. As listeners, we're used to stories where mysteries are resolved, where contradictions are explained away, where clarity eventually arrives. Science does that sometimes, but not always quickly, and not always in a straight line. More often, it proceeds by noticing small inconsistencies and refusing to ignore them. The story we are beginning tonight is not about failure. It is about precision. It is about what happens when our tools become good enough to reveal cracks in our understanding. The universe is not misbehaving. It is behaving exactly as it always has. It is our descriptions that are being tested. You might find it comforting to know that this kind of disagreement is not unusual in science. Many of the most important advances began as small tensions between theory and observation. The orbit of Mercury did not quite match predictions. The behaviour of light did not fit classical expectations. In each case, the mismatch was not a mistake to be erased, but a clue pointing towards something deeper. So when we say that the universe disagreed with itself, what we really mean is that our measurements are asking a question we do not yet fully know how to answer. There is no urgency here. The cosmos has been expanding for billions of years. It will continue doing so whether we resolve this puzzle tomorrow or a century from now. This gives us permission to slow down, to explore the problem carefully, and to accept uncertainty as part of the process. For now, it is enough to sit with the idea that even with all our technology, all our equations and all our confidence, the universe can still surprise us. It can still whisper, gently but persistently, that there is more to understand. Long before anyone suspected that space itself could stretch, the night sky appeared calm, orderly, and reassuringly still. If you stepped outside on a clear evening centuries ago, you would have seen the same familiar patterns humans had always seen. Stars rose in the east, set in the west, and returned again the next night in nearly the same places. Constellations held their shapes. The heavens felt permanent, like a painted ceiling arching endlessly overhead. Nothing about that quiet, repeating display suggested motion on the grandest scale imaginable. For most of human history, the idea that the universe could be changing in any deep structural way would have felt unnecessary, even strange. Change belonged to Earth. Seasons shifted, rivers moved, lives began and ended. The sky, by contrast, seemed immune to all of that. Philosophers and astronomers alike described the cosmos as eternal and unaltered, a backdrop against which human affairs played out. Even when planets wandered slowly against the stars, their motions were predictable, looping back again and again, as if following carefully rehearsed paths. This sense of cosmic stillness carried well into the age of early telescopes. When astronomers first began pointing lenses upward, they discovered far more detail than the naked eye could see, but not yet any sign that the universe itself was growing. They found moons around Jupiter, rings around Saturn, and faint cloudy patches that would later be called nebulae. These discoveries expanded the known contents of the universe, but they did not fundamentally change its perceived behaviour. Space, as far as anyone could tell, was simply there. Even as physics advanced, the assumption of a static universe lingered. When gravity was formalised into precise mathematical laws, it described how objects moved within space, not how space itself might behave. Stars pulled on one another, planets orbited, everything fit comfortably within a cosmic framework that felt stable and unchanging. The universe had structure, but no apparent storyline. That began to shift quietly in the early 20th century, not through philosophy or speculation, but through measurement. Astronomy was becoming more quantitative. Telescopes were larger, photographic plates more sensitive, and spectroscopy was opening a new way of reading light. Instead of simply recording where objects were, astronomers could now examine how their light was distributed across different wavelengths. Hidden within those patterns were clues about motion, composition, and distance. Light, it turned out, was far more informative than it appeared. When light passes through a prism or diffraction grating, it spreads out into a spectrum, revealing dark or bright lines corresponding to specific elements. These spectral lines act like fingerprints, allowing scientists to identify what stars and galaxies are made of. But they also do something else. They shift. If an object is moving toward us, its spectral lines shift slightly toward shorter wavelengths, a phenomenon known as blue shift. If it is moving away, they shift toward longer wavelengths, creating a red shift. At first, these shifts were used mainly to study stars within our own galaxy. Astronomers measured how fast stars orbited the Milky Way's centre, or moved relative to the Sun. The idea that entire galaxies might be moving, let alone that space itself might be stretching, was not yet on the table. Then attention turned outward. Those faint nebulae, once thought to be clouds of gas within the Milky Way, began to reveal their true nature. Some were spiral-shaped, others elliptical, and their light showed patterns that did not quite match what was expected from nearby objects. As distances were estimated more carefully, it became clear that many of these objects lay far beyond the boundaries of our own galaxy. They were galaxies in their own right, vast collections of stars separated from us by enormous gulfs of space. With that realization, the scale of the universe expanded dramatically. The Milky Way was no longer the entirety of existence. It was one island among countless others, scattered across a cosmic ocean. Once galaxies were recognized as independent systems, their motions became a subject of interest. When astronomers examined their spectra, they noticed something remarkable. the vast majority of galaxies showed redshifted light. Not just a few, almost all of them. And the farther away a galaxy appeared to be, the greater its redshift tended to be. This pattern was subtle at first and easy to misinterpret. Measurement errors were common, distances were uncertain. Yet as data accumulated, the trend became harder to ignore. Galaxies were not merely moving randomly, they seemed to be receding from us in an organised way. This observation did not immediately lead to the conclusion that the universe was expanding. In fact, the idea initially felt counterintuitive. If galaxies were moving away, where were they moving from? Was our location special? Were we at the centre of some enormous explosion? The answer, as it slowly emerged, was far stranger and far more elegant. To understand it, imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No single dot sits at the centre of the expansion. From any one dot's perspective, all others appear to be receding. The motion is not through the surface, but of the surface itself stretching. In this analogy, the balloon surface represents space, and the dots represent galaxies. The expansion of the universe works in a similar way, though without an edge or an outside. Space itself stretches, carrying galaxies along with it. They are not flying through space away from a central point. The space between them is increasing everywhere at once. This idea required a shift in how people thought about motion and distance. It also required a willingness to let go of the comforting notion that the cosmos was static. The universe was not a fixed stage. It was dynamic, evolving, changing over time. Importantly, this expansion was not something anyone had set out to find. It emerged from careful observation and reluctant acceptance. Astronomers did not wake up one morning expecting the universe to be growing. They noticed patterns, checked them, argued over them, and gradually realised that the simplest explanation involved expansion. Theory followed observation. Around the same time these measurements were being made, equations describing gravity on cosmic scales were being developed. When applied to the universe as a whole, those equations naturally allowed for solutions in which space expanded or contracted. A static universe turned out to be unstable, requiring delicate balancing to remain unchanged. Once that mathematical door was opened, the observational evidence gained a theoretical home. What is striking is how calm this realisation was. There was no single dramatic announcement that changed everything overnight. Instead, understanding accumulated slowly. Papers were published, distances recalibrated, spectra remeasured. Gradually, the idea that the universe was expanding became not just plausible, but unavoidable. For anyone living through that transition, the night sky must have taken on a new character. Those quiet points of light were no longer fixed markers in an eternal arrangement. They were participants in a grand, ongoing process. Every photon arriving at a telescope carried evidence that space itself had been stretching during its journey. This realization also introduced a new way of thinking about cosmic history. If the universe was expanding now, then in the past it must have been smaller, denser, and hotter. Expansion implied a beginning of sorts, not necessarily a moment in time that could be easily described, but a direction, a narrative. The cosmos had a past that was meaningfully different from its present. Yet at this stage, the focus was not on origins, it was on measurement. How fast was the universe expanding? Could that speed be quantified? Could it be used to estimate the universe's age or predict its future? Early attempts to answer these questions were crude by modern standards. Distances were uncertain by large factors. Estimates of expansion varied widely. Some implied a universe younger than the Earth itself, an obvious problem. Others suggested much longer timescales. Precision was elusive. Still, the core idea held. The universe was not static. The night sky was not frozen. Something vast and subtle was unfolding across incomprehensible distances. As decades passed, techniques improved. Astronomers developed better ways to gauge distances, building what became known as a distance ladder. Nearby objects could be measured directly using geometry. Those measurements calibrated brighter objects that could be seen farther away. Step by step, the reach extended deeper into space. Each rung of that ladder depended on the one below it. Any error could propagate upward. This made astronomers cautious, meticulous, and sometimes frustrated. But it also gave them confidence that, with enough care, the expansion of the universe could be pinned down numerically. Throughout all of this, one assumption remained largely unquestioned. No matter how it was measured, the expansion rate should be the same. Different methods might be noisy or imprecise, but as errors shrank, they should converge on a single value. The universe, after all, was one universe. That assumption would eventually be tested. At this point in the story, it is worth pausing to notice how quietly transformative this period was. There were no images of expansion, no animations, no sweeping visuals, just faint smudges on photographic plates, tiny shifts in spectral lines, and long nights spent comparing numbers. The universe revealed its growth not through spectacle, but through patience. Even now, when we speak of expansion, it is easy to imagine something dramatic. Galaxies rushing apart, space tearing open. In reality, the expansion is gentle on human scales. Bound systems like galaxies, solar systems, and atoms are unaffected. The stretching happens in the vast emptiness between structures, where gravity is weak and distances are enormous. This subtlety is part of why it took so long to recognise. Expansion does not announce itself loudly. It reveals itself only when you look far enough and measure carefully enough. As our understanding deepened, the expanding universe became a foundation of modern cosmology. It framed questions about dark energy, cosmic fate, and the large-scale structure of space. It also set the stage for the puzzle we are slowly approaching, the realization that measuring this expansion is not as straightforward as once hoped. For now, though, it is enough to sit with the idea that the night sky is not a static dome, but a dynamic, stretching expanse. Every distant galaxy is slightly farther away than it was a moment ago. Every beam of light arriving at Earth has been subtly altered by the growth of space along its path. This knowledge does not change the way the stars look to the eye. The constellations remain familiar. The darkness remains deep. But beneath that calm surface, the universe is in motion, expanding steadily, carrying with it the seeds of both understanding and confusion. At the beginning of the 20th century, astronomy was changing its character. It was becoming less about careful sketches and philosophical debate, and more about data, photographs, and measurement. Telescopes were growing larger. Glass plates were replacing the human eye as the final authority on what the sky contained. And quietly, almost without ceremony, the universe was preparing to reveal that it was far bigger and far less settled than anyone had imagined. Edwin Hubble entered this moment of transition without the air of a revolutionary. He was not trying to overturn cosmic assumptions or rewrite the nature of reality. In fact, much of his early work was methodical to the point of seeming ordinary. He observed, catalogued, compared, and classified. Yet it was precisely this steady, careful approach that allowed something extraordinary to emerge. Before his work reshaped astronomy, the prevailing view was still deeply uncertain about the true scale of the cosmos. The Milky Way was known to be large, but how large was unclear. Those faint spiral-shaped nebulae scattered across the sky were especially puzzling. Some astronomers argued they were nearby clouds of gas, forming stars within our own galaxy. Others suspected they might be distant systems of stars in their own right, but proof was elusive. The disagreement was not trivial. If those nebulae were inside the Milky Way, then our galaxy might be the bulk of the universe. If they were outside it, then the universe was vastly larger than anyone had comfortably accepted. Resolving this question required not opinion, but distance. And distance, in astronomy, is one of the hardest things to measure. Hubble's contribution began with a type of star that, at first glance, looks unremarkable. Cepheid variable stars are pulsating stars whose brightness rises and falls in a regular cycle. What makes them special is a simple, reliable relationship between how fast they pulse and how bright they truly are. By observing how bright a Cepheid appears from Earth and comparing it to how bright it must actually be, astronomers can calculate its distance. This relationship had been discovered earlier, but Hubble was among those who applied it decisively to the problem of the nebulae. Using powerful telescopes, he identified Cepheid variables within the Andromeda Nebula. When he calculated their distances, the result was unavoidable. Andromeda was far beyond the boundaries of the Milky Way. In that moment, the universe expanded dramatically in the human imagination. The Milky Way was no longer the whole story. It was one galaxy among many, separated from others by distances so large they strained comprehension. What had once seemed like faint smudges were now understood as enormous systems of stars, each containing billions of suns. This discovery alone would have secured Hubble's place in astronomical history, but it was only the beginning. Once galaxies were recognised as independent entities, a new question arose naturally. How were they moving? Were they drifting randomly, held loosely by gravity, or was there some larger pattern at work? Answering this required combining distance measurements with information about motion, and once again, light provided the key. By studying the spectra of galaxies, astronomers could determine whether their light was shifted toward the red or blue end of the spectrum. These shifts indicated motion away from or toward the observer. When Hubble compared the distances of galaxies with their redshifts, a pattern began to emerge. The farther away a galaxy was, the faster it appeared to be receding. At first, this relationship was tentative. The data were noisy, distance measurements were still uncertain, and redshifts could be misinterpreted. But as more galaxies were added to the sample, the trend grew clearer. There was a roughly linear relationship between distance and recessional velocity. Double the distance, and the speed at which the galaxy was moving away roughly doubled as well. This was not the behaviour one would expect from galaxies simply flying outward through static space. Instead, it suggested something more profound. Space itself was stretching, carrying galaxies along with it. The universe was expanding uniformly, not from a single centre, but everywhere at once. This relationship would later be formalised into what is now known as Hubble's law. It provided the first quantitative evidence that the universe was not static, but dynamic, changing over time. The night sky, long thought to be fixed, was revealed as part of an unfolding process. It is worth emphasising how restrained this conclusion was at the time. Hubble himself was cautious. He spoke of apparent velocities and observational correlations, not cosmic origins or explosive beginnings. The idea that expansion implied a denser past was not his primary focus. His work was grounded in what the data showed, and the data showed a consistent stretching. That restraint mattered. Science advances most reliably when claims stay close to evidence, and Hubble's careful phrasing allowed others to build upon his results without overextending them. Theoretical physicists could take the observational relationship and explore its implications, while astronomers continued refining the measurements themselves. One of the remarkable features of this discovery is how it avoided spectacle. There was no visual sign of expansion. Galaxies did not appear to move from one night to the next. The effect revealed itself only through careful comparison of numbers gathered over long periods. It was the kind of discovery that rewards patience rather than excitement. As measurements improved, the slope of the distance-velocity relationship became increasingly important. This slope represented the expansion rate of the universe. A steeper slope meant faster expansion. A shallower one implied slower growth. Determining this value accurately became a central goal of observational cosmology. Early estimates of the expansion rate varied widely. Some suggested a universe only a few billion years old, which conflicted with geological evidence from Earth. Others implied much older ages. These discrepancies were not surprising given the challenges involved. Each distance measurement depended on calibrations that could introduce systematic errors. Still, the basic picture held. Galaxies farther away were receding faster. Space was stretching. This realization quietly reshaped how humanity understood its place in the cosmos. The universe was no longer a static container in which events happened. It was an active participant, evolving alongside the matter and energy within it. The past was not just different in detail, but fundamentally different in scale and density. Yet for all its significance, this expansion did not feel dramatic in daily life. The solar system remained stable, atoms remained intact, gravity held galaxies together internally. Expansion operated on scales so vast that it was invisible except through careful analysis. This made it easy to accept intellectually without feeling emotionally unsettling. Over time, Hubble's work became a cornerstone of modern cosmology. It set the stage for later discoveries, including the cosmic microwave background and the accelerating expansion driven by dark energy. But it also introduced a subtle dependence on measurement technique that would later become important. The expansion rate was not something directly observed in a single experiment. It was inferred through a chain of reasoning that connected light, distance, and motion. Each link in that chain had its own uncertainties. As techniques improved, Astronomers revisited earlier assumptions, recalibrated distances, and refined models. For many years, this process moved steadily toward convergence. Estimates of the expansion rate narrowed. Confidence grew. The sense was that the universe's behaviour was being pinned down more precisely with each new dataset. And yet, embedded within that progress was the possibility of disagreement. Because as measurements became more precise, small differences mattered more. Two methods that once seemed consistent within large error margins could begin to diverge as those margins shrank. A discrepancy that would have been invisible decades earlier could become impossible to ignore. This is where the legacy of those first measurements becomes especially relevant. The relationship Hubble uncovered did not specify how the expansion rate might change over time, nor did it guarantee that all methods of measuring it would agree perfectly. It simply established that expansion existed and that it followed a measurable pattern. The universe, it turned out, was more nuanced than a single number could capture easily. As you let this settle in, there is no need to hold on to the technical details. What matters is the arc of the story. A careful observer measures distances. Those distances reveal a pattern. That pattern transforms our understanding of the cosmos, and embedded within that transformation is the seed of a future puzzle. The expanding universe, once revealed, becomes something we want to understand ever more precisely. We refine tools, we extend reach, we compare methods, and in doing so, we discover that the universe does not always give the same answer twice in the same way. Light does not arrive quietly. Even when it looks soft to the eye, even when it barely lifts itself out of the darkness, it carries an extraordinary amount of information. Every photon that reaches a telescope has a history. It remembers where it came from, how energetic it was when it began its journey, and how that energy changed as it travelled across space. Long before anyone understood the universe was expanding, that memory was already embedded in the light itself, waiting to be read. To appreciate why redshift became such a powerful clue, it helps to slow down and think about what light really is. Light behaves as a wave, stretching and compressing as it moves. The distance between those stretches is called wavelength. Short wavelengths correspond to higher energy light, like blue or ultraviolet. Longer wavelengths carry less energy and appear redder. This is not an artistic description. It is a physical property that can be measured with precision. When light is emitted by an atom, it does so at very specific wavelengths. Each element produces a distinct pattern, a set of lines that appear at exact positions when the light is spread into a spectrum. These patterns are reliable. Hydrogen always produces the same lines. So does oxygen, sodium, iron, and every other element found in stars and galaxies. This consistency is what allows astronomers to identify the composition of distant objects. But those same lines can shift. If a source of light is moving toward an observer, the waves get slightly compressed, pushing the wavelengths toward the blue end of the spectrum. If the source is moving away, the waves stretch out, shifting toward red. This effect had been understood in sound long before it was applied to light. A passing siren sounds higher in pitch as it approaches and lower as it recedes. Light behaves in an analogous way, though the effect is far subtler and requires careful measurement. In the early days of spectroscopy, astronomers noticed these shifts in stars. Some stars showed blue shift, others red shift, indicating motion within the Milky Way. These observations were useful, but they did not yet hint at anything cosmic in scale. Stars orbit within galaxies. Motion was expected. The surprise came when this same technique was applied to galaxies beyond the Milky Way. When astronomers examined the spectra of distant galaxies, they found something striking. The familiar spectral lines were still there, unmistakable in their pattern, but they were displaced. Almost without exception, they were shifted toward the red. The farther away the galaxy appeared to be, the farther its lines were shifted. At first, this could be interpreted as ordinary motion. Perhaps galaxies were simply moving away from us through space. But that explanation quickly grew uncomfortable. Why would nearly all galaxies be receding? And why would their speeds increase so smoothly with distance? This is where redshift stopped being a curiosity and became a revelation. If the redshift were caused only by galaxies moving through static space, then our location would be special. We would be near the centre of some grand dispersal, watching everything flee outward. Yet observations did not support a preferred direction or centre. From every vantage point examined, the pattern looked the same. Galaxies receded from each other uniformly. A different interpretation fit better. Space itself was stretching, and light travelling through that space was being stretched along with it. As a photon crossed the universe, the fabric of space gently expanded, increasing the photon's wavelength. By the time it reached us, it appeared redshifted, not because the galaxy was racing away through space, but because the space between us and the galaxy had grown during the photon's journey. This idea takes a moment to sink in, and it is perfectly fine if it feels unintuitive. We're used to thinking of motion as something objects do. Expansion, in this sense, is something space does. Galaxies are not the primary actors, they are passengers. Redshift, then, became a way of reading the universe's expansion history. Measure how stretched the light is, and you can infer how much space expanded while the light was travelling. Combine that with an estimate of distance, and you gain insight into the rate at which the universe is growing. What makes this especially powerful is that redshift can be measured with extreme precision. Spectral lines can be identified to many decimal places. Even tiny shifts can be detected. This allowed astronomers to quantify recessional velocities long before they had equally precise distance measurements. In practice, this meant that redshift data accumulated quickly and reliably. Distances, by contrast, remained stubbornly difficult. You could measure a galaxy's redshift accurately, but translating that into a precise distance required additional assumptions and methods. This imbalance shaped cosmology for decades. At low redshifts, relatively nearby galaxies, the relationship between redshift and distance appears linear. Double the distance, double the redshift. This simple relationship made it tempting to treat redshift as a proxy for distance. In many cases, that approximation worked reasonably well. However, redshift is not just a measure of distance, it is also a measure of time. When you observe a highly redshifted galaxy, you're seeing it as it was when the universe was much younger. The light left the galaxy billions of years ago, when space was denser and expansion behaved differently. As a result, redshift encodes information not only about where something is, but when it is. This dual role complicates interpretation. A given redshift does not correspond to a single fixed distance in a simple way. It depends on the expansion history of the universe, which in turn depends on its contents, matter, radiation, and whatever else may be influencing cosmic growth. Early on, these complications were not fully appreciated. The first uses of redshift focused on establishing expansion, not on extracting fine details. But as precision increased, the subtleties became unavoidable. Another important distinction emerged between different kinds of redshift. There is the familiar Doppler redshift, caused by motion through space. There is gravitational redshift, caused by light climbing out of a gravitational well. And there is cosmological redshift, caused by the expansion of space itself. In the nearby universe, these effects can overlap. Untangling them requires careful modelling. For distant galaxies, cosmological redshift dominates. The stretching of space overwhelms local motions. This makes redshift an especially clean probe of large-scale behaviour. Yet it also means that interpreting redshift correctly depends on having a reliable model of how the universe expands. Here, a quiet circularity appears. To understand redshift, you need to know the expansion history. To determine the expansion history, you rely on redshift. This is not a flaw, but it does mean that assumptions matter. Different assumptions can lead to slightly different conclusions. As astronomers pushed their observations deeper, they encountered light that had been stretched dramatically. Galaxies at high redshift appeared faint, small, and distorted by intervening matter. Their spectra shifted far into the red and infrared. Observing them required new instruments and new techniques. Despite these challenges, redshift measurements remained among the most reliable tools available. They provided a consistent, repeatable way to compare galaxies across enormous spans of space and time. No matter how uncertain distances might be, redshifts could be trusted. This reliability is part of what made later disagreements so surprising. When different methods of measuring cosmic expansion began to diverge, redshift itself was not the culprit. The spectral measurements were solid. The gentle stretching of light was not in doubt. The tension arose when redshift-based inferences were combined with other measurements to produce a single number describing expansion today. In some approaches, redshift data were interpreted through models that traced expansion from the early universe to the present. In others, redshift was paired with direct distance indicators in the nearby universe. Both used the same fundamental phenomenon, the stretching of light, but in different contexts. The fact that they did not agree suggested that the issue lay not with redshift as an observation, but with how its meaning was being translated into a single, present-day expansion rate. There is something almost poetic in that. Though we will keep our feet firmly on the ground, light travels faithfully. It stretches exactly as space stretches. It does not introduce ambiguity on its own. The ambiguity enters when we ask it to answer questions that depend on everything else the universe has been doing along the way. For listeners, it may be comforting to remember that redshift is not an abstraction invented to confuse. It is a direct, measurable feature of light. Astronomers do not imagine it. They record it. They see spectral lines displaced in ways that can be quantified precisely. The challenge lies in interpretation, not detection. As instruments improved, redshift surveys mapped millions of galaxies, revealing the large-scale structure of the universe. Filaments, voids, clusters, all traced through the systematic stretching of light. These maps confirm that expansion is not chaotic. It is remarkably uniform on large scales. Uniform does not mean simple, though. When you trace redshift back far enough, you encounter the early universe where conditions were radically different. Matter and radiation interacted intensely. Expansion rates changed over time. Dark energy, whatever its nature, became dominant only relatively recently in cosmic history. This means that the redshift you observe today is the result of a long cumulative process. It is not a snapshot of motion at a single moment, but a record of everything that happened along the photon's path. It is enough to appreciate the quiet power of this phenomenon. A gentle reddening of light, almost imperceptible to the eye, revealed that the universe is not standing still. It is stretching steadily and everywhere, carrying with it galaxies, histories, and questions that grow more interesting the closer we look. Knowing that the universe is expanding is one thing. Figuring out how fast it is expanding is something else entirely. The difference between those two questions may seem subtle at first, but it is where cosmology shifts from a broad realization to a precise science. Expansion by itself is a concept. Expansion with a number attached becomes a test of our understanding of reality. Once astronomers accepted that galaxies were receding from one another, because space itself was stretching, the next natural step was to quantify that stretching. How much space was added over a given amount of time? Was the expansion gentle or rapid? Did it proceed at a steady pace, or did it change as the universe aged? These were not philosophical questions, they were numerical ones, and answering them required building a ruler large enough to span the cosmos. On Earth, measuring speed is straightforward. You mark a distance, measure how long it takes to cross, and divide one by the other. In the universe, neither part of that equation comes easily. Distances are enormous and indirect. Time spans billions of years. Nothing can be tracked continuously from start to finish. Instead, astronomers are forced to infer speed by comparing snapshots taken at different distances, which also correspond to different moments in the past. This is where the idea of a cosmic ruler begins. The basic insight behind measuring expansion speed is simple. If you can determine how far away a galaxy is, and you can measure how fast it is receding from us, then you can calculate the rate of expansion. Do this for many galaxies at many distances, and a pattern emerges. The slope of that pattern is the expansion rate. In practice, every part of this process is challenging. Measuring how fast a galaxy is receding is the easier half. Redshift provides that information directly. The shift in spectral lines can be translated into a velocity with high precision. For nearby galaxies, this velocity behaves much like an ordinary speed. For distant galaxies, it reflects the cumulative expansion of space. Either way, redshift gives astronomers a reliable handle on motion. Distance, however, is far more elusive. You cannot simply look at a galaxy and know how far away it is. Brightness alone is not enough, because galaxies come in many sizes and luminosities. A small nearby galaxy can appear similar to a large distant one. To untangle this, astronomers rely on objects whose true brightness is known, or can be inferred, allowing apparent brightness to be converted into distance. This is the foundation of what is often called the cosmic distance ladder. The metaphor is apt, because each method of measuring distance builds on the previous one. You start close, with techniques that work only in the nearby universe. Those calibrate methods that reach farther. Those in turn enable measurements at truly cosmic scales. The lowest rungs of this ladder rely on geometry. For nearby stars, astronomers can use parallax, the apparent shift in position as Earth moves around the Sun. This method is simple in principle and extremely reliable, but it only works for stars relatively close to us. Beyond that, the shift becomes too small to detect accurately. Once distances to nearby stars are known, they can be used to calibrate other indicators, such as certain types of variable stars whose intrinsic brightness follows predictable patterns. These objects act as standard candles, cosmic light sources with known wattage. Measure how dim they appear, and you can infer how far away they must be. Each step outward introduces more uncertainty. Dust can dim light, stellar populations can vary, calibration errors can creep in. Astronomers are acutely aware of these issues and spend enormous effort correcting for them. Still, no rung of the ladder is perfect. The strength of the method lies in careful cross-checking and redundancy. Once distances to nearby galaxies can be measured, redshift data can be paired with those distances. Plotting recessional velocity against distance reveals a line. The slope of that line is what we call the Hubble constant. It tells us how many kilometers per second of recessional speed correspond to each megaparsec of distance. Although the units may sound arcane, the idea is straightforward. The larger the Hubble constant, the faster the universe is expanding today. A smaller value implies slower expansion. Early measurements of this number were wildly uncertain. Initial estimates placed it far higher than modern values, implying a universe much younger than it actually is. Over time, as distance measurements improved, the estimated expansion rate decreased and stabilized. By the late 20th century, astronomers believed they were closing in on a reliable value. This progress created a sense of confidence. The cosmic ruler, while imperfect, seemed to be improving steadily. Each new generation of telescopes refined distances, reduced errors, and tightened constraints. The expectation was that all reasonable methods would eventually agree. That expectation turned out to be premature. As techniques improved, two broad approaches to measuring expansion speed emerged. One focused on the nearby universe, building the distance ladder step by step and pairing those distances with redshift measurements. The other relied on observations of the early universe, using relic radiation to infer how expansion must have proceeded over cosmic time. Both approaches were sophisticated. Both were grounded in well-tested physics, and both were supported by extensive data. Yet they did not produce the same answer. Before we reach that disagreement directly, it is important to understand just how much effort went into refining the cosmic ruler. This was not a matter of a few astronomers disagreeing casually. It involved decades of work, thousands of observations, and constant re-evaluation of assumptions. One source of difficulty lies in the fact that the universe is not empty. Matter bends light. Dust absorbs it. Galaxies cluster together under gravity, introducing local motions that can slightly distort redshift measurements. Separating the smooth expansion of space from these local effects requires careful statistical treatment. Another complication is that the expansion rate is not truly constant over time. The Hubble constant describes the expansion rate today, but the universe expanded at different speeds in the past. Matter slowed expansion early on. Later, dark energy caused it to accelerate. Translating observations made at different cosmic epochs into a single present-day number requires a model of how expansion evolved. This means that measuring the expansion rate is not just an observational challenge. It is also a theoretical one. Observations must be interpreted within a framework that describes how the universe behaves over time. In the nearby universe approach, this framework plays a relatively small role. Distances are measured directly. Redshifts are interpreted locally. The expansion rate emerges from data with minimal extrapolation. In the early universe approach, the framework is essential. Observations of ancient light must be translated through a model to predict what the expansion rate should be today. This introduces dependence on assumptions about the universe's contents and behaviour. For a long time, these two approaches were consistent within uncertainties. Differences existed, but they were small enough to be attributed to measurement error. As data quality improved, those uncertainties shrank. Instead of converging, the results drifted apart. At first, this was uncomfortable, but not alarming. Cosmology has seen many apparent discrepancies resolve themselves with better understanding. Astronomers are trained to suspect systematics, subtle biases that affect measurements in ways that are hard to detect, a miscalibrated distance scale, an overlooked effect of dust, a statistical assumption that breaks down at high precision. Teams re-examined their methods, they tested alternative calibrations, they compared independent datasets. The cosmic ruler was scrutinized from every angle. What made the situation increasingly puzzling was that improvements did not erase the discrepancy. Each side became more confident in its result. The error bars became smaller, the disagreement became clearer. This was not a case of one method being sloppy and the other precise. Both were careful, both were internally consistent, both used the same fundamental physics of redshift and light. The ruler itself was not broken. The question was whether it was being applied to the same universe in the same way. There is something quietly profound about this moment in science. For generations, astronomers struggled simply to measure cosmic distances at all. Now they had reached a point where they could measure them well enough to uncover tensions that hint at deeper issues. Precision had become a double-edged sword. From a broader perspective, this is exactly how scientific understanding advances. When measurements are crude, many theories can coexist. As measurements sharpen, some ideas are ruled out. Occasionally, the data challenge the framework itself. The expansion rate of the universe sits at the intersection of observation and theory. It depends on how we read light, how we build distance scales, and how we model cosmic history. A disagreement here does not point to a small oversight. It points to something fundamental. Still, there is no rush to judgment. The universe is under no obligation to match our expectations. It may be that subtle effects remain unaccounted for. It may be that our models, while broadly correct, need refinement, or it may be that something genuinely new is at play. For now, what matters is that the cosmic ruler exists, and that it has revealed a surprising result. The universe can be measured. Its expansion can be quantified. And when we do so with enough care, the numbers tell a story that is not yet finished. Measuring distance in the universe requires a certain kind of humility. You cannot reach out and mark the space between galaxies. You cannot pace it off or bounce a signal there and back in any practical way. Instead, you have to rely on what the universe offers freely: light, repetition, and consistency. This is where standard candles enter the story, not as poetic objects but as practical tools, quiet benchmarks that allow astronomers to turn faint glows into numbers. The idea behind a standard candle is straightforward. If you know how bright something truly is, and you can measure how bright it appears to be, then the difference between those two tells you how far away it must be. Light spreads out as it travels. Double the distance and the brightness drops by a predictable amount. This relationship is not negotiable. It is built into geometry itself. The challenge, of course, is finding objects whose true brightness you can trust. Most things in the universe are unreliable in this sense. Stars vary in size, temperature, and age. Galaxies contain wildly different numbers of stars and amounts of dust. Even objects that look similar can differ enormously in how much light they produce. Without some internal reference, apparent brightness alone tells you very little. Standard candles are different because they come with a built-in guarantee. Their intrinsic brightness can be determined independently of distance. That makes them cosmic yardsticks, objects that allow astronomers to lay down a scale across space, one step at a time. One of the earliest and most important classes of standard candles comes from a type of star whose behaviour is not random at all. Cepheid variable stars brighten and dim in a regular repeating cycle. The key insight, discovered through painstaking observation, is that the period of this cycle is directly related to the star's true luminosity. Slow pulsations mean higher brightness. Faster pulsations mean lower brightness. This relationship was uncovered by Henrietta Leavitt in the early 20th century, while she was studying photographic plates of stars in nearby galaxies. At the time, the significance of her finding was not fully appreciated, yet it would become one of the foundational tools of modern cosmology. Once this relationship was established, Cepheid variables became immensely valuable. Measure how long a Cepheid takes to brighten and dim, and you know how bright it truly is. Compare that to how bright it appears from Earth, and the distance follows. These stars are luminous enough to be seen in nearby galaxies, but not so bright that they dominate their surroundings. They occupy a sweet spot visible across millions of light years, but still common enough to be found in significant numbers. This made them ideal for extending the distance ladder beyond the Milky Way. Still, Cepheids have limits. They cannot be seen at the farthest reaches of the universe. Their light fades into the background long before you reach the most distant galaxies. To push farther, astronomers needed a brighter candle. That candle arrived in the form of stellar explosions, Type 1. As supernovae are among the most luminous events in the universe. For a brief period, a single exploding star can outshine an entire galaxy. What makes these explosions especially useful is their remarkable consistency. They occur when a white dwarf star reaches a critical mass and undergoes a runaway nuclear reaction. Because that critical mass is nearly the same in every case, the resulting explosion has a predictable brightness. This does not mean every Type 1a supernova is identical. There are small variations, but these can be corrected for by studying the shape of the light curve, how quickly the explosion brightens and fades. With these corrections applied, Type 1a supernovae become extraordinarily reliable standard candles. Unlike Cepheids, supernovae can be seen across billions of light years. They allow astronomers to measure distances deep into the universe, far beyond the reach of individual stars. In many ways, they form the backbone of modern distance measurements. The relationship between these different standard candles is crucial. Cepheids are used to measure distances to nearby galaxies. Those distances calibrate the true brightness of supernovae observed in the same galaxies. Once supernova brightness is calibrated, they can be used to measure distances much farther away. This layering is why the distance ladder metaphor matters. Each rung depends on the one below it. If the lower rungs are unstable, the entire structure wobbles. If they are secure, the ladder extends confidently outward. Astronomers are acutely aware of how sensitive this process is. A small error in the calibration of Cepheids can propagate into a larger error in supernova distances. That, in turn, affects measurements of the universe's expansion rate. For this reason, enormous effort has gone into refining these calibrations. Space-based telescopes have played a critical role here. Observing Cepheids from above Earth's atmosphere reduces distortion and allows for more precise measurements of brightness and period. This has helped tighten uncertainties and improve confidence in distance estimates. Even so, complications remain. Dust is one of the most persistent challenges. Dust between stars and galaxies absorbs and scatters light, making objects appear dimmer than they truly are. If not accounted for correctly, this can make distances seem larger than they are. Astronomers correct for dust using colour information and models of how dust behaves, but these corrections are never perfect. Another issue is environment. Cepheids in different galaxies may differ slightly in composition. Supernovae occurring in different stellar populations may have subtly different properties. Each of these factors can introduce small biases that only become apparent at high precision. For a long time, these issues were thought to be under control. Independent teams using different datasets and methods arrived at similar expansion rates when relying on standard candles. The consistency was reassuring. It suggested that the cosmic ruler, while complex, was fundamentally sound. As measurements improved further, however, something unexpected happened. The distances derived from standard candles, when paired with redshift measurements, consistently implied a faster expansion rate than that inferred from observations of the early universe. This was not a single anomalous result. It appeared across different studies, using different telescopes, different samples of stars and supernovae, and different analysis techniques. The agreement among local measurements was strong. The disagreement with early universe predictions was persistent. This placed standard candles at the centre of a growing puzzle. If the nearby universe was expanding at one rate, and the early universe implied a different rate, then something had to give. Either the standard candles were subtly misleading, or the interpretation of early universe data was incomplete, or the universe itself was behaving in a way not fully captured by existing models. From the perspective of the standard candle approach, confidence was high. Cepheid physics is well understood. Supernova explosions are studied in detail. Calibration techniques are tested repeatedly. While no measurement is perfect, the level of agreement within the local universe is difficult to dismiss. Yet science does not operate on confidence alone. It operates on consistency across methods. This is where the tension becomes interesting rather than troubling. Standard candles are not isolated measurements. They're embedded within a network of observations that include redshift surveys, galaxy clustering, and background radiation. When one part of that network disagrees with another, it signals an opportunity to learn. It is also worth remembering that standard candles do not measure expansion directly. They measure distance. Expansion enters when distance is compared to redshift. This means that any systematic issue affecting either side of that comparison can influence the result. Astronomers have explored numerous possibilities. Could Cepheids be affected by unseen companions? Could supernovae evolve subtly over cosmic time? Could dust behave differently in distant galaxies? Each idea has been investigated carefully. So far, none has resolved the discrepancy fully. This does not mean the standard candles are wrong. It means they are precise enough to raise questions that were invisible before. In that sense, they are doing exactly what good scientific tools should do. They are revealing the limits of our current understanding. As a listener, you do not need to hold all these details at once. The important idea is simple. The universe provides certain objects whose behaviour allows us to measure distance reliably. These objects form the backbone of one way of determining how fast the universe is expanding. That way produces a clear, consistent answer. The surprise is that another equally careful method produces a different one. Standard candles flicker steadily, indifferent to the debates they inspire. They pulse and explode according to the same physical laws they always have. The light they emit travels faithfully across space, carrying information we are still learning how to interpret. Long before the universe could be measured in billions of light years, it had to be measured in something much smaller and far more familiar. Before expansion rates, background radiation, or competing numbers entered the conversation, astronomers faced a simpler but more stubborn problem. They needed to know how far away anything was at all. Without distance, motion had no scale, brightness had no meaning, and the night sky remained a flat map with no depth. The first true steps outward did not begin with galaxies or explosions or ancient light. They began with stars that refused to shine steadily. Cepheid variable stars do not behave like most stars. Instead of glowing at a constant brightness, they rhythmically brighten and fade over and over again, with periods ranging from a few days to several weeks. This pulsing is not random or chaotic. It follows a precise physical process tied to the structure of the star itself. Layers within the star expand and contract, trapping and releasing energy in a repeating cycle that can continue for millions of years. At first, these stars were curiosities, catalogued for their odd behaviour, but not yet understood as tools. Their importance only became clear once astronomers noticed something remarkable. The rhythm of a Cepheid's pulse was directly linked to how much light it truly produced. Slow, long pulses meant a very luminous star. Faster pulses meant a dimmer one. This relationship was stable, repeatable, and universal. Once that connection was recognised, Cepheids transformed astronomy. For the first time, astronomers had access to stars whose true brightness could be determined without knowing their distance beforehand. Measure the period of the pulse, and the intrinsic luminosity follows. Compare that intrinsic brightness to how bright the star appears from Earth, and distance emerges naturally. This was revolutionary not because it was flashy, but because it was reliable. Unlike many astronomical techniques, Cepheid distance measurement did not depend on complex modelling of galaxies or assumptions about cosmic history. It relied on stellar physics that could be tested locally. Cepheids in our own galaxy could be studied in detail. Their distances could be verified using geometric methods. Once calibrated nearby, the same relationship could be applied to Cepheids in other galaxies. This calibration step was crucial. Astronomers first used parallax to measure distances to the nearest Cepheids. Parallax, the apparent shift in a star's position as Earth orbits the Sun, is a purely geometric effect. It does not depend on brightness, models, or assumptions about stellar behaviour. It is as close to a gold standard as astronomy can achieve. With those nearby distances in hand, the period-luminosity relationship could be anchored securely. Cepheids became the first rung of a cosmic distance ladder that could extend far beyond the Milky Way. When astronomers began identifying Cepheids in nearby galaxies, everything changed. Those faint points of light were no longer just stars, they were mile markers in space. This is how the universe first acquired depth. Before Cepheids, galaxies could be ranked by apparent size or brightness, but those rankings were ambiguous. A small nearby galaxy could appear similar to a massive distant one. Cepheids broke that ambiguity. They provided absolute distances, revealing that some objects lay far beyond the Milky Way, while others were much closer than assumed. This was the method that allowed astronomers to establish that spiral nebulae were actually entire galaxies. It was the first time humanity could confidently say, this object is millions of light years away, and mean it numerically. Once distances to galaxies were known, redshift measurements gained context. A galaxy's spectral shift could now be paired with a distance that was not guessed but calculated. Plot enough of these pairs, and the expansion of the universe revealed itself. This is why Cepheids sit at the foundation of expansion measurements. They are not glamorous compared to supernovae or background radiation, but they are indispensable. Without them, the nearby universe remains uncalibrated, and every higher level measurement floats without anchor. Still, Cepheids are not perfect. They exist only in certain types of galaxies, those with ongoing star formation. They are bright, but not infinitely so. Beyond a certain distance, even the largest telescopes struggle to isolate them from surrounding starlight. Crowding becomes an issue, dust becomes an issue, resolution becomes an issue. Astronomers have spent decades addressing these challenges. Observing Cepheids from space avoids atmospheric distortion. Careful statistical methods correct for blending with nearby stars. Observations in infrared wavelengths reduce the impact of dust. Each refinement sharpens the ladder. What makes Cepheids especially important in the current context is not just that they provide distances, but that they link different measurement regimes together. Cepheids connect geometric measurements in our local neighbourhood to supernova measurements in distant galaxies. They are the hinge on which the entire local distance scale turns. If Cepheids are miscalibrated, everything above them shifts. For this reason, Cepheid studies are among the most scrutinised in astronomy. Independent teams analyse the same stars using different techniques. Distances are cross-checked with alternative methods where possible. Systematic uncertainties are catalogued exhaustively. Despite this scrutiny, Cepheid-based distances have proven remarkably stable. As measurements improved, the distances derived from Cepheids did not wander wildly. They converged. Different groups, using different data sets and methods, arrived at closely matching results. This consistency is one reason astronomers place so much confidence in the local distance ladder. And it is precisely this confidence that makes the present disagreement so striking. When Cepheid-calibrated distances are used to measure the expansion rate of the nearby universe, the resulting number is consistently higher than the value inferred from early universe observations. This is not a marginal effect. It persists across data sets and refinements. If Cepheids were unreliable, the problem would be easier. But their behaviour is well understood, their calibration repeatedly tested, and their results internally consistent. This has led astronomers to ask uncomfortable but necessary questions. Could Cepheids behave differently in other galaxies than they do locally? Could metallicity, the abundance of heavier elements, subtly affect their brightness? Could unresolved companions skew measurements? Each possibility has been examined carefully. Metallicity does have an effect, but it is small and already accounted for. Companion stars can introduce bias, but corrections reduce this impact significantly. None of these effects appear large enough to explain the full discrepancy. This does not mean Cepheids are beyond question. It means that questioning them has so far reinforced their reliability rather than undermined it. Another important point is that Cepheids do not operate in isolation. They are part of a chain. Parallax calibrates Cepheids. Cepheids calibrate supernovae. Supernovae measure expansion. If something were fundamentally wrong with Cepheids, inconsistencies would appear elsewhere in the ladder as well. So far, they have not. This is why the current tension cannot be dismissed as a simple measurement error. The first rung of the ladder appears solid. The higher rungs are independently strong. Yet when the ladder is compared to a completely different approach, that does not rely on stars at all, the numbers disagree. In a way, Cepheids have done their job too well. By enabling precise local measurements, they have exposed a mismatch that cruder tools would have hidden. There is also something quietly human about this part of the story. Cepheids pulse patiently, indifferent to cosmological debates. They have been doing so long before humans existed and will continue long after. Their regularity is not for us, but we have learned to use it. As listeners, it can be comforting to think of these stars as steady companions in an otherwise confusing universe. They flicker predictably, providing reference points in a cosmos that is otherwise difficult to measure. Yet even these steady beacons cannot tell the whole story alone. Cepheids measure distances out to tens of millions of light years. That is vast by human standards, but small compared to the observable universe. Beyond that range, astronomers must rely on brighter indicators, objects that can be seen across much greater distances. Those brighter indicators depend on Cepheids for calibration, but they introduce new physics, new uncertainties, and new opportunities for discovery. By the time astronomers reach the limits of what individual stars can tell them, the universe does not politely stop offering clues. Instead, it provides something far more dramatic. Stars that do not merely flicker or pulse, but end their lives in explosions so bright they briefly overwhelm the darkness around them. These events are rare, violent, and fleeting, yet they have become some of the most important tools for measuring the universe on its larger scales. Supernovae enter the story not as accidents, but as necessities. Cepheid stars allow astronomers to measure distances to nearby galaxies with confidence, but beyond that range, their light simply fades into the background. Even the most powerful telescopes struggle to isolate individual stars at extreme distances. To continue outward, something brighter is required, something that can be seen across hundreds of millions, even billions of light years. Supernovae provide exactly that. A supernova is not a single phenomenon, but a category of stellar death, encompassing several different physical processes. Massive stars can collapse under their own gravity and rebound violently, tearing themselves apart. Other stars meet their end in quieter but equally destructive ways, accumulating matter until a critical threshold is crossed. Among these various endings, one type stands out for its usefulness as a cosmic measuring tool: Type 1. A supernovae occur when a dense stellar remnant, known as a white dwarf, gains too much mass. This can happen through interaction with a companion star or the merger of two white dwarfs. Once the mass crosses a precise physical limit, the star can no longer support itself. A runaway nuclear reaction ignites, and the star detonates. What makes this process remarkable is its consistency. Because the critical mass at which the explosion occurs is nearly the same every time, the resulting explosion releases a predictable amount of energy. That energy translates into a characteristic brightness. While individual events vary slightly, those variations follow patterns that can be measured and corrected for. Once those corrections are applied, Type 1a supernovae behave as reliable standard candles. For a brief period, often a few weeks, a single supernova can shine as brightly as the billions of stars in its host galaxy combined. This makes it visible across vast distances, far beyond the reach of Cepheids. Where Cepheids provide the first rung of the distance ladder, supernovae extend it outward dramatically. The process works like this. Astronomers first observe Cepheid stars in a nearby galaxy. Though Cepheids establish the distance to that galaxy with high confidence, if a Type 1a supernova occurs in the same galaxy, its apparent brightness can be compared to the known distance. That allows astronomers to determine the supernova's true brightness. Once that true brightness is calibrated, Type 1a supernovae observed in much more distant galaxies can be used to measure distances far beyond the local universe. The ladder continues upward, one explosion at a time. This handoff between Cepheids and supernovae is one of the most carefully studied transitions in cosmology. It has been refined repeatedly, tested across different environments, and scrutinized for hidden biases. The reason is simple. Supernovae sit at the heart of local expansion measurements. If something is wrong here, the consequences ripple outward. For many years, this method performed beautifully. When distances derived from supernovae were compared to redshift measurements, the relationship was clear and consistent. Galaxies farther away showed larger redshifts, indicating faster recessional motion. The slope of that relationship yielded an expansion rate that seemed stable and repeatable. Then something unexpected happened. As more supernovae were observed at greater distances, astronomers noticed not just expansion, but acceleration. Distant supernovae appeared dimmer than expected, suggesting that the universe's expansion had been speeding up over time. This discovery led to the idea of dark energy, a mysterious component that drives accelerated expansion. This result was profound, but it also reinforced confidence in supernova measurements. Independent teams using different samples and methods arrived at the same conclusion. The supernova data were not chaotic or contradictory. They told a coherent story. That coherence is important when considering the present tension. When supernova-calibrated distances are combined with Cepheid measurements and redshift data, the expansion rate inferred for the nearby universe consistently comes out higher than the value inferred from early universe observations. This result is not fragile. It does not depend on a single dataset or a single analysis choice. It emerges repeatedly. To challenge it, astronomers have examined supernovae from every angle. They have asked whether supernovae in distant galaxies behave differently than those nearby. Could stellar populations evolve in ways that subtly affect explosion brightness? Could dust in distant galaxies dim light in unexpected ways? Could selection effects bias which supernovae are detected? Each of these questions has been investigated carefully. Supernova-like curves are studied in detail, not just peak brightness, but the entire rise and fall of the explosion. These curves encode information about the physics of the event and allow corrections that standardize brightness. Comparisons across redshift show no evidence of large, unaccounted-for evolution. Dust is a persistent concern, but multi-wavelength observations help disentangle dust effects from intrinsic brightness. Statistical methods account for selection bias, ensuring that brighter, easier-to-detect supernovae do not skew results artificially. While small uncertainties remain, none appear large enough to explain the full discrepancy. This is what makes supernovae so central to the current puzzle. They are not new, poorly understood tools. They are mature, well-tested instruments of measurement. Their consistency across space and time is precisely why they revealed cosmic acceleration in the first place. If supernovae were fundamentally unreliable, the discovery of acceleration itself would be suspect. Yet that discovery has withstood decades of scrutiny. There is also an important conceptual point here. Supernovae do not measure expansion at a single moment. They sample it across a range of distances and times. Nearby supernovae reflect recent expansion. Distant ones probe earlier epochs. When analysed together, they trace how expansion has evolved. In the local universe, where supernovae overlap with Cepheid-calibrated distances, the expansion rate they imply is clear. It is faster than what early universe models predict. This raises an intriguing possibility. Perhaps the universe's expansion history is more complex than currently assumed. Perhaps something subtle changes between early and late times. Supernovae, by bridging those epochs, may be highlighting that transition. It is also worth remembering that supernovae are independent of many assumptions that affect other measurements. They do not rely on early universe physics. They do not depend on conditions shortly after the Big Bang. They measure distance and redshift directly, here and now, using objects that exist in the present universe. That immediacy gives their results a particular weight. From a broader perspective, there is something fitting about this. The most violent events in the universe, the deaths of stars, have become tools for understanding its larger-scale behaviour. Destruction, in this case, illuminates structure. As listeners, it is not necessary to track every correction or statistical nuance. The essential idea is simpler. Supernovae are extraordinarily bright, remarkably consistent explosions that allow astronomers to measure distances across much of the observable universe. When those distances are compared to redshift, they reveal how fast the universe is expanding nearby. That speed does not match what we infer from looking deep into the past. Supernovae do not resolve the disagreement, they sharpen it. They stand between Cepheid stars and ancient background light, connecting the local universe to cosmic history, and in doing so, they insist that the numbers derived from nearby measurements are not easily dismissed. Does not describe a particle, a force, or does not describe a particle, a force, or a specific object. Instead, it summarizes the present behavior of the entire universe. It tells us, in compact form, how quickly space itself is expanding right now. At first glance, that might sound like an abstract curiosity, the sort of thing that matters only to specialists, but the consequences of this number extend much farther than its definition suggests. The value assigned to the Hubble constant influences estimates of the universe's age, the size of the observable cosmos, the growth of structure, and the balance between matter, radiation, and dark energy. Change the number slightly, and the universe you infer changes with it. This is why disagreement over the Hubble constant is not a technical footnote. It is a signal that something important may be unresolved. To understand why this number carries such weight, it helps to return briefly to what it represents. The Hubble constant links distance and recessional speed. For every additional megaparsec of distance between us and a galaxy, there is an additional amount of recessional velocity caused by cosmic expansion. Multiply the distance by the Hubble constant, and you get the expected expansion-related speed. Despite the word constant, this value is not fixed across cosmic time. The universe expanded at different rates in the past. Matter slowed expansion early on. Dark energy accelerated it later. The Hubble constant refers specifically to the expansion rate today at the current age of the universe. This distinction matters because different measurement methods do not all sample the same epochs. Some measure expansion directly in the nearby universe. Others infer it indirectly by modelling how the universe evolved from its earliest observable state. In principle, both approaches should converge on the same present-day value. In practice, they do not. When astronomers using Cepheid stars and supernova measure the Hubble constant locally, they obtain a value that suggests a relatively fast expansion today. When astronomers use early universe observations and project forward using well-tested models, they obtain a lower value, implying slower expansion. The difference is not subtle anymore. It exceeds what can reasonably be attributed to random error, and because both approaches are internally consistent, the disagreement cannot be dismissed casually. This has led to a great deal of careful thinking about what the Hubble constant actually encodes. One immediate consequence of its value is the inferred age of the universe. A faster expansion rate today generally implies a younger universe, all else being equal. A slower expansion suggests more time has passed since the universe was much denser. While this relationship is not perfectly linear, the dependence is strong enough that differing Hubble constant values lead to age estimates that differ by hundreds of millions of years. Those differences matter because they must be consistent with independent age estimates. The oldest stars in the Milky Way, for example, provide a lower bound on the universe's age. Any cosmological model must allow enough time for those stars to form and evolve. If the Hubble constant were too large, the implied universe could be younger than its own contents, an obvious problem. Modern measurements avoid that extreme conflict, but the margin is not large. A higher Hubble constant pushes the universe toward the younger end of what stellar ages allow. A lower value provides more breathing room. The Hubble constant also affects the inferred size of the observable universe. The faster space expands, the farther light has travelled since the beginning. This influences how much of the universe we can, in principle, observe. It shapes estimates of cosmic horizons and the scale of large structures. Beyond size and age, the Hubble constant plays a role in understanding how galaxies and clusters formed. Structure formation depends on how quickly matter could clump together under gravity before expansion pulled things apart. A faster expansion rate today suggests a different balance between gravity and expansion over time, which in turn affects how structures grow. Because of these connections, the Hubble constant is woven deeply into cosmological models. It is not a standalone parameter that can be adjusted freely without consequences. Change it, and other pieces must adjust as well. This interconnectedness is part of what makes the current tension so informative. It is not just that two numbers differ. It is that each number fits comfortably within a different but internally coherent picture of the universe. On the local side, the picture is grounded in direct measurement. Cepheids pulse, supernovae explode, distances are calculated, redshifts are measured. The expansion rate emerges from data that describe the nearby universe as it exists now. On the early universe side, the picture is grounded in physics that has been tested repeatedly in other contexts. The behaviour of matter and radiation in the early universe is well understood. The equations that describe how small fluctuations grow into large structures are robust. When these are applied to early universe observations, they predict a specific expansion history, including a present-day Hubble constant. Neither picture is ad hoc, neither is obviously flawed. This is why the Hubble constant has become a focal point rather than a peripheral detail. It sits at the intersection of observation and theory, and at that intersection, something does not line up. It is tempting to think of this as a failure of measurement, but that framing is misleading. Measurements are doing exactly what they should do. They are precise enough to reveal inconsistencies that were previously hidden. The discomfort arises not because the data are unreliable, but because they are reliable enough to disagree meaningfully. Another way to think about the Hubble constant is as a diagnostic tool. It tests whether our model of the universe, which includes dark matter, dark energy, and known forms of radiation, is complete. If all components are correctly identified and described, then independent measurements should converge. If they do not, then either something is missing or something is being misinterpreted. This does not mean the model is wrong in a dramatic sense. It may be incomplete in subtle ways. A small additional component, a slight modification to how energy behaves, or an overlooked interaction could reconcile the numbers. Alternatively, the resolution may lie in measurement after all, but at a deeper level than initially expected. Perhaps there is a systematic effect that affects local distance measurements in a correlated way. Perhaps early universe interpretations rely on an assumption that needs refinement. The challenge is that many obvious possibilities have already been examined and found wanting. Astronomers have varied analysis techniques. They have used different samples, they have tested alternative calibrations, they have looked for environmental effects. None of these efforts have erased the discrepancy. As a result, the Hubble constant has taken on a role it was never intended to have. It has become a probe of new physics. This does not mean that new physics is guaranteed. Science is cautious by design. Extraordinary claims require extraordinary evidence. At present, the evidence says that there is a persistent, statistically significant tension. Interpreting that tension is an ongoing process. It is also worth noting that the Hubble constant is not the only parameter in cosmology. Many others describe the universe's contents and behaviour. What makes the Hubble constant special is that it can be measured in conceptually simple ways. Distance and speed are intuitive quantities. When disagreement arises here, it feels especially striking. It may help to think of the Hubble constant as a summary of everything that came before. Cepheids establish distances, supernovae extend those distances, redshift measures motion, combine them, and you get a number. That number, in turn, must align with what we infer from the universe's earliest light. When it does not, the discrepancy does not live in isolation. It echoes backward through the entire measurement chain and forward into theoretical interpretation. This is why discussions of the Hubble constant are rarely just about the number itself.